So in our previous lesson, we looked at the power rule. And the power rule is one of the most commonly used differentiating techniques that we will apply to almost every function in some form. Now, another powerful differentiating technique we're going to use is something called the chain rule, right? And essentially what the chain rule is it allows us to differentiate more complicated functions where we have a function which is inside another function. And so what we are basically going to do is we're going to string together a set of derivatives in a specific way, which we'll look at in a second. So to understand what we're talking about, let's just consider some function f of x. And let's say f of x is the function 2x plus 3. And then we have some other function, which is g of x, which we could say perhaps is x squared. Now, if we wanted to create a composite function from the two of these, let's say we have the composite function g f of x. So in other words, do f first and then do g. So we're going to put f into g essentially. So g f of x would be f, which is this function here, and it'll go inside this function here, which is something squared. So here's the function f, and by squaring we have the function g. So this is what we call a composite function. Okay, we have a function inside a function. Now, if we wanted to differentiate this new function, right, at the moment we don't have a technique for that. However, this is just a quadratic. We could very easily just expand this out. So for simplicity's sake, we can just change this into y equal to, and we can expand out and get 4x squared plus 12x plus 9. And so if we wanted to differentiate this with respect to x, in other words, we want dy by dx, we can just use the power rule. So we can multiply by the power. So we're going to multiply by anything in front of x. So we'll get 8x and reduce the power by 1. It becomes 1, and plus 12 for the next one, etc. Right? And the constant is obviously 0. So in this case, where we had a function inside a function, it was very easy for us to just expand this out and differentiate using the power rule that we've learned previously. Now, that's not always going to be the case. So let's consider this function here. So here we have a function 2x plus 3, except instead of being put into a function g of x, which was x squared, this has gone into a function which was x to the power 8. Now, we could use our knowledge of the binomial expansion to expand this out, and then we could differentiate each of the terms separately. However, that is very cumbersome, and what we're going to do is we're going to come up with a better way of differentiating this. So let's say, for instance, this is some equation y equal to 2x plus 3 to the power of 8. So in order to use the chain rule, we're going to use a technique called substitution. So we're going to substitute the term inside the brackets for another variable. So let's call it u. So we're going to say let u equal 2x plus 3. So instead of having 2x plus 3 in a bracket to the power of 8, we can substitute in this u, and so what we have on the other side is y equal to u to the power of 8, okay? Which, if you look at, we can use the power rule on. So we can actually use the power rule on both of these functions now to differentiate them. And that's exactly what we're going to do. So we're going to differentiate u equal to 2x plus 3 with respect to x, right? So we're going to have, instead of dy by dx, we will now have du by dx. So differentiating this with respect to x, we differentiate the first term. We have a power of 1 multiplied by the power. The derivative here is 2, and 3 is a constant, so its derivative is 0. Then we're going to differentiate this expression here. We have dy equal to u to the power of 8. So we're going to differentiate u or dy or y with respect to u. Okay, so we're just replacing x now with u. Okay, so when we differentiate now u, all right, since we are differentiating with respect to u is now the variable that we are differentiating. So we can use the power rule on this, and we can get 7, my apologies, we get 8 multiplied by the power, and then reduce the power by 1. So now we have the derivatives of these two functions that one we've created and one we've substituted. So in order to calculate the derivative of the original function, we're going to use something called the chain rule. We're going to chain these derivatives together to give us what we originally wanted. So what we originally want is dy on dx. That's the derivative of this function here. So by chaining things together, we can say if we want dy by dx, right? What we need to do is we need to take this du on dx, and if we multiply this by this dy on du, what we notice is the u's will cancel out, the du's will cancel out, and we'll get exactly what we want, dy on dx. And so that's exactly what we're going to do. We're going to go dy on dx is equal to, well, du on dx is 2, and dy on du was this 8u to the power of 7. So we're going to simplify this expression and get 16u to the power of 7. And then we need to resubstitute what u actually was, because we didn't want an expression with u, we wanted something with y and x. So we will substitute back our original substitution, which was 2x plus 3. And so we'll get 16 2x plus 3 to the power of 7. And that is essentially what we are doing when we use the chain rule, right? Now, once we do the chain rule over and over and over again, we're going to start noticing a pattern. So there's an alternative way that we can use the chain rule once we've done it a few times. So the encouragement is do a few where we do substitution, and once we've done the substitution a few times, we start noticing this pattern. So let's take our function y equal to 2x plus 3, and we can actually do the substitution in our head. What we did when we let u equal to the function on the inside is we essentially differentiated the inside function, all right? And then we differentiated the outside function. So if we just ignore the fact that this is 2x plus 3 in a bracket and we just think of it as one thing, we were basically differentiating that thing as itself, right? So the way you can think about this is differentiate the outside, so if we differentiate the outside, just ignore the 2x plus 3, just pretend that that's some other variable. And we're going to differentiate that thing. So we're going to drop the power down to the front, so multiply by the power. And then we're going to reduce the power by 1. So that's the outside derivative. And then we're going to think, what's the inside derivative? So we're going to differentiate the inside essentially. So the inside is 2x plus 3. When we differentiate 2x plus 3, we just get 2. And then we're going to multiply together. So we're going to take 8, 2x to the power, or 2x plus 3 to the power of 7. We're going to multiply it by 2. And we will get our 16, 2x plus 3 to the power of 7. So let's look at another example. Here we have the equation y equal to 2 over 5x squared minus 1 to the power of 4. And we can not expand this out and easily differentiate this, so we have to use a better technique. Now, we can't differentiate things when we have stuff like this stuck. Well, we can. Well, we don't know the technique now. But at the moment, we can't differentiate this. So what we need to do is we need to bring this up to the numerator. So we're going to change our equation into y equal to 2, 5x squared minus 1 to the power of minus 4. So I'm going to show both ways again. One where we're going to use a substitution, and one where we're going to use intuition. So we basically use the substitution, but we're doing the substitution intuitively. So using substitution, what we need to do is, instead of having this mess of 5x squared minus 1, we're going to say, well, let's just let u equal that mess on the inside. Okay? And then what I can do is I can just differentiate that. So I have u equal to something, so I'm going to have du on dx. So I'll just differentiate that using the power rule. So multiply by the power. So we'll get 10x, reduce the power by 1. Minus 1 is a constant, and so there's no derivative. Now back to our original equation. We changed all that mess on the inside to u. So we have y equal to 2u to the minus 4. And so we can just use the power rule to differentiate this. So we will have dy on du. So once again, using the power rule, there's the power. So multiply down by the power, we're going to get minus 4 times 2, which is minus 8, u, and then we're reducing the power by 1, so it becomes minus 5. So be careful when you have negative indices. Then we're going to chain them together. We want dy on dx. Okay, so when we want dy on dx, we need to take this du on dx, and we need to multiply it by dy on du, so that the du's can cancel out. So we have an expression for du on dx, and we have an expression for dy on dx. So we'll have 10x, and we're going to multiply that by minus 8u to the power of minus 5. And then we're going to just multiply everything out and then resubstitute our value for u. Okay, because again, remember, we didn't want u, we just changed something into u, and we need to put it back at the end. So minus 8 times 10 is going to give us minus 80x. We're going to put back our substitution, so 5x squared minus 1 to the power of minus 5. And we can, if we want, we can tidy this up by going minus 80x all over 5x squared minus 1 to the power of 5. Now let's look at the intuitive way of doing this. So we want to remember that this is the inside function. So this part here is the inside function. And this whole thing here, if we ignore the bracket and just pretend it's a variable, is the outside function. So we're going to differentiate the outside first. So the outside function is going to be 2 something to the minus 4. So we're going to multiply by the power. So we're going to get minus 4 times 2 is minus 8. And then we're going to reduce the power by 1. And now we're going to differentiate the inside. So the inside is 5x squared minus 1. So if we differentiate that, we're going to get 10x. And now we're going to multiply the two together. Okay, so we're going to get minus 8 times 10x. So we'll get minus 80x. And I can already see that this part here can just go down to the denominator. Okay. So again, like I said, once you've done the substitution method a few times, you will notice that there's a pattern, and so you can rather do it intuitively. So basically what we say is differentiate the outside and multiply by the derivative of the inside. And that's essentially what the chain rule is. at one more example of the chain rule. Here we're asked to find the gradient of a curve y equal to 8 over x minus 2 squared at the point where the curve crosses the x-axis, right? So if we want to find the gradient of something, this isn't a gradient function, this is the curve itself. If we want to find gradient, we need to find the gradient function, so we need to differentiate. At the moment, this equation is not in a form that we can differentiate, so we're going to change this into y equal to 8 x minus 2 to the power of minus 2. And now we're going to find the gradient function, so dy on dx. Okay, so we can either substitution or we can just use intuition. So I'm going to use intuition. So I'm going to say I'm going to take the derivative of the outside. So the derivative of the outside is going to be multiply by the power, which is minus 2. So minus 2 times 8 is minus 16. And then I'm going to reduce the power by 1. So I'm going to get minus 3. And then I'm going to multiply by the derivative of the inside. So if I look on the inside function, the derivative is, or the function is x minus 2, and the derivative would here just be 1. And so our derivative, or our gradient function, dy on dx is just equal to minus 16 over x minus 2 cubed. Okay, the rest of the question is quite easy. They say find the gradient at the point where the curve crosses the y-axis. The point where the curve crosses the y-axis is where x is equal to 0. So when x is equal to 0, we get minus 16 over 0 minus 2 cubed, right, which is minus 8. So 16 minus 16 divided by minus 8 is going to give us 2. So the gradient at the point x equal to 0 of this function is 2. So just as a final recap, the chain rule is essentially where we are chaining together the derivatives because of substitution. However, it's better that we start thinking about the chain rule as a systematic process so that we can differentiate it using it a lot faster.